Hello students, so in this lecture we will be discussing about elastic modulus and especially in the case of nanomaterials. Now, elastic modulus is proportional to the bond strength of the material, and higher bond strength it means that you have a higher elastic modulus and also the melting point of the material is high. Now, if we consider the two atoms which are coming together to form bond, and the plot of the force between these two atoms is something like this, with r is the distance of separation. Now double differentiation of this force at the equilibrium position r0, which is sometimes called the mean position or the bond length, is actually equal to the elastic modulus. Now this elastic modulus is therefore is depending upon the atomic bond strength and is independent of the structure as well as the macrostructure of the molecule concerned, since it is mainly depending upon the bond strength. Now, as an increase in temperature causes vibrations of the atoms, and there is a shift of mean position of the bond. That means there is increase in R0. So this actually leads to a decrease in elastic modulus. Also, increase in defect is considered to be analogous to an increase in temperature, and that's why increase in defect is supposed to decrease the elastic modulus of the material. Now, nanomaterials they usually have high defect. By high defect, we mean that the intercrystalline regions, the IC regions, that is the triple junction, grain boundaries, and quadruple nodes, they are high. So this is from the previous understanding. This will cause a decrease in elastic modulus. Plotting elastic modulus with the reference value of the bulk, what can be seen is that there is a decrease of elastic modulus, and this elastic modulus decreases by 30 to 50% in comparison to the bulk. As previously said, as in nanocrystalline materials, the volume fraction of the grain boundary is high, and grain boundaries are supposed to have a lower elastic modulus because there is no perfect bonding between them, there is no homogeneous bonding between the atoms. So this actually causes a reduction of elastic modulus in nanocrystalline materials. Now, uh, polycrystalline materials, which if we take a general consideration that polycrystalline materials, the grain elastic modulus is depending dependent upon this parameter alpha, which is delta d by t, where delta d is the grain boundary width and d is the grain diameter. So this is the expression to get the overall elastic modulus. Now, if we analyze this consideration, what we can see is that these are the grains of this is the dimension of the grains, and these are the grain boundaries. So this factor, which is a significant factor, uh, in the case of nanomaterials, this is significant only when the size of the grains are less than 10 nanometers, because then only this factor becomes significant. Otherwise, since usually in the case of polycrystalline materials, D is much larger than 10 nanometers, and therefore this delta D is also this ratio is also very small, so it will not have any significant effect. Only when the size is reduced to a certain level, that means let's say 10 nanometers, this factor becomes significant, and the effect of elastic modulus can be seen. Effect on elastic modulus can be seen. However, since nanomaterials can be of different types, it has been observed that this reduction of elastic modulus has also been found for a higher diameter, higher grain size. And a possible explanation of this is that porosity, increase in porosity, which takes place while synthesis of nanomaterials, and the synthesis and this porosity is inadequate sometimes. So this is mainly due to inadequate sintering. That is the process of making the atoms or the to form and coalesce into larger atoms. This process of sintering, which is mainly found in ceramics, is inadequate, and so there are some porosity existing in the fabricated nanomaterials, which may cause a decrease in elastic modulus for even the grain size each more than 10 nanometer or higher grain size. Now, to formulate the effect of porosity, this is the formula where a change in porosity with respect to the original porosity has been framed, and effective porosity is predominant for grain size less than 20 nanometer, and effective porosity decreases the elastic modulus by 20 to 30%. However, it has been observed that the elastic modulus, although it may decrease with decrease in nanometer, decrease in grain size, but in some nanomaterials like carbon nanotubes, the opposite effect has been observed, that decreasing this diameter of the tube, which is found by either a zigzag or an armchair nanotube, the elastic modulus has found to increase. This is mainly due to the surface tension which is existing in the carbon nanotube. It gives an extremely high strength. So lower is the diameter, the higher is the elastic modulus in case of a carbon nanotubes.